Hey, welcome back. And today we are gonna be looking at arenes. So arenes are aromatic compounds that have a continuous layer of p orbitals sideways overlapping each other and causing the delocalization of pi electrons across the structure. So one such example of an arene is benzene. So I'll draw a benzene for you. And as you can see, each of the carbon atom are actually sp2 hybridized because there's a trigonal planar structure in each of the carbon, whereby there are three bond pairs and one lone pair. So end up it will have three sp2 hybrid orbitals with a unhybridized p orbital that is acting perpendicular to the sp2 hybrid orbitals of the carbon. So and all these p orbitals of carbon atoms will sideways overlap to form a ring of the localized pi electron cloud that is above and below the aromatic structure. So all these are your pi bonding electron clouds. Yes. So we look at the reactivity for benzene is that they are generally very reactive to electrophiles because they have a region of high electron density, and that high electron density is originated from the very large pi electron cloud that I just mentioned, because the double bonds in the benzene ring always alternates. And for the second bullet point is to explain why substitution occurs instead of addition. And the main reason is to retain the aromatic stability of the aromatic structure of benzene. And in order to achieve such a resonance stability, we would have to have the pi electrons from the CC double bonds or the CC pi bonds to be delocalized across the structure, and that's how you achieve your resonance stability. The last bullet point explains why arenes or benzene are generally less nucleophilic than alkenes, and that is because they are resonance stabilized and involve delocalization of pi electron, unlike alkenes, whereby your alkenes they have the pi electrons are actually localized in the CC double bond, and they do not have resonance stabilization because the p orbitals there's only two p orbitals that are involved in the sideway overlap compared to benzene. Now we'll look at also one more reason is that you can see that for benzene um there are generally three CC bonds, which means that there are in total 6 pi electrons. And as you know that since all these 6 pi electrons are delocalized, that means each of the CC, each of the 6 CC bonds in benzene will get 1 pi electron each. So each one will get 1 pi electron each. Okay? Whereas for your alkenes, because it's localized, so there's 2 pi bonding electrons. Alright, so now we're gonna look at some of the reactions that arenes undergo. This is a summary. As usual, you can just take a look yourself. Then the first reaction is involving electrophilic substitution of your halogens onto the benzene ring. So as you can see, the physical state is the physical state of halogens are under standard conditions, and we use anhydrous aluminum chloride catalyst, iron 3 chloride catalyst, or iron catalyst. And you have to make sure that they are anhydrous so that your aluminum chloride or iron chloride won't get hydrolyzed in water to form a acidic solution. And this what's important about these catalysts is that they are actually Lewis acids, or you can say electron pair acceptors. And these are important because you want to generate your stronger electrophile, which is Cl plus. And how you do that is that the Cl-Cl bond pair will be donated to the Lewis acid, which is aluminum chloride. And how it achieves it is because aluminum has energetically accessible and vacant orbitals. Same goes for iron. So because this is the energetically accessible vacant orbitals is what allows it to accept the bond pair of electron from chlorine so that it can generate this stronger electrophile that is positively charged, unlike chlorine gas. Okay? You need to generate a stronger electrophile because benzene is not as nucleophilic as your alkene. Okay? So that is why you use anhydrous catalyst, because if you hydrolyze in water, that means you will have the following species being formed, and thus your aluminum or iron is unable to act as a Lewis acid anymore, and it unable to generate the stronger electrophile. So we see room temperature and pressure is being used over here, and since it's a substitution reaction, you will see the hydrogen of the benzene being substituted by the halogen. And as usual, your observations are according to what the chemical equation says. So write out the chemical equation and write the observation from there. So mechanism, I show you the mechanism sort of. So you can see that the chlorine bonding pair is being accepted by the aluminum atom to form both chlorine, uh, the positively charged chlorine cation, as well as this species right here. I'll draw it at the bottom. See, and this whole thing is negatively charged. Okay, because the chloride anion is being added onto the aluminum chloride. So slow step is because it involves the heterolytic fission of a CC pi bond, and it is also the second step is a fast step because it involves the electrostatic force of attraction between the positively charged carbocation as well as the negatively charged AlX4. This is the mechanism for methyl benzene with chlorine. Do take note that the very first step is a reversible arrow. Okay. Okay, the second reaction right here is showing the uh it's a Friedel-Crafts alkylation reaction. So we are using it's a useful step up reaction if you want to add more carbon to a certain organic compound. So we're gonna use the reagents. As you can see from the chemical equation, we are using CH3 CH2Cl. So the same thing, we use anhydrous AlCl3 catalyst, FeCl3 catalyst, and Fe catalyst. FYI, Fe catalyst can be used. Actually, for this case, I would say Fe catalyst is not recommended unless you are using. Let me edit this. Fe catalyst is recommended to use if you are using the halogen reaction. So in this case, from the above, your Fe catalyst can be used because it can react with chlorine gas to form FeCl3, or you can react with bromine liquid to form FeBr3. But for this case, it because we are not using the halogen gas, that's why it's preferable if we use FeCl3 or AlCl3. Room temperature condition and observation are as such. Just take note that the positive charge must be on the carbon that is positively charged. And you can see over here that the circle of this circle is facing towards the carbon that is tetrahedral. So this is the carbon that is tetrahedral right here. So this circle must point towards it. It is to show that there are 5 carbon atoms. It is to show that there are 5 carbon atoms that are involved in the delocalization of pi electron. So this, and this, they all are sp2 hybridized and have the p orbitals that sideway overlap to cause delocalization of pi electrons. So in this case, actually there are 4 pi electrons that are being delocalized across the 5 carbon atoms. So just take note of that. And you can see that the AlCl4 catalyst, it uses a lone pair of electrons to abstract the proton so that the CH bonding electron can form back the CC double bond. Okay, for this special case over here is intramolecular electrophilic substitution. So we are gonna have um a hydrogen atom being substituted out by a chlorine atom, and we're gonna have a nucleophile attacking an electrophile within the organic molecule itself. So in this case, same right here, we are not using Fe catalyst because it's useless. Alright, so the chemical equation right here, we would identify when you encounter this type of scenario where you never encountered before, we identify which one is the nucleophilic region and which one is the electrophilic region. And it's always the mechanism is always the same. It's about electron rich always going towards the electron poor or electron deficient regions. So identify nucleophile as well as electrophile. Or you can also say Lewis base or Lewis acid. Okay, so in this case, our benzene ring is gonna be the bad boy here, so it's gonna be the nucleophile, and the electrophile, or in the sense the victim, is gonna be this this group over here. And so you can see that the polar C double bond O will be able is very polar to the point that we will have a partial positive on the carbon and partial negative on the oxygen. And it is like that because the carbon is attached to two highly electronegative groups that are oxygen and chlorine, which decreases the electron density on the carbonyl carbon. So in this case, we're gonna have uh, an attack from the benzene ring, the high electron cloud of the benzene ring, to the electrophilic electron deficient carbonyl carbon. Okay, so that is the main concept. As you can see over here, because we are using AlCl3 to make a stronger electrophile, so we would get rid of the Cl atom right here to form our stronger electrophile right here. So to make the carbonyl carbon to be a positively charged carbon. And then we will see that the nucleophile attacks the electron deficient carbonyl carbon. And the other steps are the same as the steps that we have gone through before. Okay, so for this reaction is a nitration reaction. So we'll use concentrated H2SO4 and concentrated HNO3 heat under reflux at 55 degrees Celsius. So the chemical equation is just take note that there's no H2SO4 involved here because a nitration reaction involves the addition of NO2 group onto the benzene ring. So that would mean that we'll use nitric acid as our reactant right here, and H2O will be our product that will be formed. Just take note that observation is not very important here, so don't have to remember it very rigidly. It's not really commonly tested. So for this, we have the mechanism. As you can see that H2SO4, how the first step works is that H2SO4 is actually a stronger acid compared to nitric acid. Okay, so in this case, what I will do is that the reason why HSO4 is deemed as a stronger acid than HNO3 is because, as you can see, after if I draw out the equation for the acid dissociation, right? We would compare the stability of the anion or the conjugate base. So in this case, you can see that the p orbital of oxygen sideway overlap with the, I would say, either the d orbital or the p orbital. I think d orbital of s atom right here. So the lone pair would delocalize into the s double bond O of your hydrogen sulfate anion. So you can see that the lone pair on the negatively charged oxygen, it can delocalize and either cause this oxygen to be negatively charged or this oxygen to be negatively charged. So you can see that in total there are 3 oxygen that can bear the negative charge, and your pi electrons can delocalize across this region. Okay? So for this part, but for nitrate ion, right, you can see that it can only delocalize among three atoms only. So the extent of the localization plays a huge role in which anion or which conjugate base is more stable. So in this case, this one is actually more resonance stabilized. Okay, so that is why H2SO4 is a stronger acid, and not just a stronger acid. Be more specific, it's a stronger Bronsted-Lowry base. Sorry, stronger Bronsted-Lowry acid. So it would be able to donate a proton. Okay, so I draw the formal charges on HNO3, and this oxygen will actually abstract a proton, okay, and it will cause HSO4 minus to form, as well as this conjugate acid of HNO3. Alright, so at the end of the day, we will cause this bond pair of NO to be pushed to the oxygen because the oxygen is positively charged. So electron rich go to electron poor to form water molecule as well as your NO2 plus. So to form your NO2 plus, you have to push. You can see this oxygen right here is negatively charged, right? So this negatively charged oxygen, so electron rich will go towards this bond right here because this N is positively charged. Then after that, this bond right here will go towards this positively charged oxygen. So as you can see, is the concept is the same. It's about electron rich to electron poor. Okay, and that is not all. Uh, because your concentrated H2SO4 is a very, very strong acid. So this water molecule will then end up be protonated by the concentrated sulfuric acid. So this will get protonated and it will form 2HSO4 minus plus H3O plus NO2 plus. Alright, so this is how you derive your first step. So most people, if they couldn't remember the first step equation, they will often forget to uh and they follow all the rules, right? They will often forget to protonate this H2O. So you just remember that concentrated H2SO4 is very strong acid. My goodness, handwriting. Okay, I'll go back to the same old page. And then you can see the NO2 plus is a strong electrophile compared to HNO3. That is why we use very harsh conditions right here, concentrated. And it's also to prevent the ionization of HNO3 into H plus and NO3 minus. If that's the case, right, then you would not have your NO2 plus electrophile being generated. That's why we have to use concentrated. Okay. And we have the temperature maintained at 55 degrees Celsius to prevent the nitration to form multi-substituted products. And since NO2 is a deactivating group, your nitrobenzene will be less nucleophilic than benzene because the electron density of benzene in nitrobenzene will be pulled away by NO2 plus by both the inductive and resonance effect. So what is going on? I can't erase this. Okay. Alright, next part is electrophilic substitution or nitration of methyl benzene. You just take note that the same everything is the same except that the condition is just 30 degrees Celsius because your methyl group is actually a strong activating, it's an activating group and it's an electron donating group. So if you can recall that the inductive effect is due to the polar CH bonds and as well as the net dipole moment acting towards the benzene ring. So because the net dipole moment act towards the benzene ring, your electron density is gonna accumulate towards carbon and that will act as an electron reservoir to donate electron density towards the benzene ring. Okay? So likewise, this is the same, just that you have to make sure that uh because the methyl group will increase the electron density on the position 2 and position 4 carbon relative to the methyl group and make sure that uh you won't have your third position 3 nitro methyl benzene being formed. So for free radical substitution over here, so this is the same concept as last time, so make sure you put whether is it limited or excess. Most of the time it should be limited because we are always producing mono substituted products. So you can see there's only one chlorine over here. Only one chlorine is being substituted. And observations are the same as before. Alright, so now we go to strong oxidation. So for strong oxidation, we'll use a common oxidizing agent that we see before, which is potassium manganate ViI. So, and we will use an acidic medium to prevent the production of MnO2 precipitate. And we use heat under reflex also. So for this case, if some people may find the balancing of the chemical equation a bit hard, so I will show you how to balance this. So first step, when you see this type of balancing equations, you always have to balance the carbon first. Balance the number of carbon. Alright? So so I know my product will be uh benzoic acid. Okay? Because for this strong oxidation or side chain oxidation, I would require a benzylic hydrogen. So as long that I have benzylic hydrogens right here, these are called benzylic hydrogens. It will straight away be oxidized. This carbon will be oxidized to a carboxylic acid. So this will be oxidized to a carboxylic acid group. And any excess carbon will be oxidized to carbon dioxide. Alright, so In this case, to balance the equation, we first know what is the product, which is benzoic acid, and then we know that one carbon dioxide molecule will be formed. Okay, so we have officially balanced the number of carbon on both sides. So 8 on the left and 8 on the right. Then next up, we would balance the charges. So in this case, we see that on both sides, there is no charges to be balanced. So it's all good, all neutral on left and right side. The third thing to take note of is to balance the number of hydrogens. So on the left side, one, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 hydrogens. And on the right hand side, we have 1, 2, 3, 4, 5, 6. 6 hydrogens. So 9 hydrogen and 6 hydrogens. So we need 3 more hydrogens. Oh wait, no. There is 10 hydrogen on the left. So that's why we need 4 more hydrogens. My bad. I was totally bombarded. Why there's 3 hydrogens? Okay, so we need 4 more hydrogens. So we balance using water molecule. Okay, and last but not least, we will balance oxygens. So oxygen, there is how many on the right hand side? 1, 2, 3, 4, 5, 6. So there's 6 oxygens in total. So we put 6 right here. And that's how you officially balance a chemical equation. Okay, so I recall with you steps 1, balance carbon. Second, balance charge. Third, balance H. And last, balance O. Alright, coming back to these observations that I shown, just a common observation that is always missed out is that benzoic acid is actually a white precipitate because you know that the bulky alkyl group is actually it is due to the bulky alkyl group that causes benzoic acid to be insoluble in water. Alright, so that's why a white precipitate is formed because uh, only ID forces can be formed between the benzene ring and water, and it's not enough, and it releases energy, and this energy is not enough to compensate the energy that is used to break the strong hydrogen bonds between either your benzoic acid molecules or your water molecules. Uh, when carbon dioxide is produced, you have to say that effervescence is observed. Okay, for remarks part, the K2Cr2O7, this is another oxidizing agent, but we can't use this because it's a weaker oxidizing agent. And these side chains, you know that CH bonds are actually very strong, so you would need to actually use a much stronger oxidizing agent. Alright, we'll move on to here. This one, I can show you this how to balance this equation. This is in the alkaline medium. Alright, so as usual, we will look back in this case example. So all is fine. Just that we have to have a alkaline medium. So alkaline medium, that means we will have to ensure that it is not benzoic acid that's formed, but it's the benzoate anion. Okay, and this carbon dioxide we will convert this to a carbonate anion. So as you can see over here, uh the first step is actually done. We balance the carbons already. There's 8 on the left, 8 on the right, but the charges are not balanced. So we will have to balance it with 3OH minus. Alright, so after we balance the 3OH minus, we'll take a look at the hydrogens. So there are 13 hydrogens on the left, and there are 1, 2, 3, 4, 5. Let me erase this. This is definitely not 6. This is on this one there's actually 5, and there's 13 hydrogens right here. So in this case, you will need 8 more hydrogens. So 8 more hydrogens, so instead of 2, we will make this 4. Okay? So now we balance oxygen, the last one, 2, 3, 4, 5, 6. 6 oxygen on the right, and we have 3 oxygen on the left. 3 oxygen on the left. So in this case, this there will be 3 of the O brackets. Okay? Okay, wait, my bad. This is wrong. I counted the oxygen wrongly. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 on the right and 3 on the left. So we will need 6 more. Okay? So this is how you balance the equation. As seen right here. Okay? Now we'll go on to this part, the extension of side chain oxidation of methylbenzene. So for the first two the first two reactions, I won't go through in depth because it is obvious that there's a benzylic hydrogen right here. So this will like I said, will readily oxidize to COOH group. And then the rest of the other groups, we would actually oxidize it to carbon. So this right here, all this will be oxidized to carbon dioxide. I will bring your attention to the third and fourth one because the third and fourth one are not very common. So how you will actually do this is that you cannot tell me that you want to oxidize the molecule right here to form two benzoic acids because that would violate the law of conservation of mass. And what do I mean by that is that if you produce these two and you count the number of carbon on both sides, you realize that there are actually 13 carbon on the left, but now you will have 14 carbon on the right if you oxidize the carbon to benzoic acid. So what we will do instead is that the benzylic hydrogen, we will convert it to a OH group. So you convert it to a OH group. Uh, and one problem is that if you can decide to convert both benzylic hydrogen into OH group. However, because there is a lot of steric hindrance because of the two bulky benzene rings, the larger electron cloud of all these will cause the whole entire molecule to be unstable. That is why we only oxidize one benzylic hydrogen to become OH, and this OH will be further oxidized to a ketone. Same goes for this benzylic hydrogen right here. We'll oxidize it to a OH group right here. And do not tell me that all these three benzene rings will undergo oxidation to form benzoic acid because that would violate this is no because it violates the conservation of mass. Okay, so now we go on to the effect of activating groups and deactivating groups. So just take note how this is actually in your data booklet. So most The only thing I'm gonna go through right here is how uh to appreciate this much better, because some people will just okay, it's not some people, but basically this entire thing is in the data booklet. As long you just flip to your data booklet and just uh answer the question according to this data booklet, everything will be fine. But what I'm gonna go through below is uh pretty much an extension. It will be a good to know if you are able to understand it. So the reactivity of this ring, for this second row, we are often talking about the rate of the electrophilic substitution. And then the third row, the position of E, it is to imply the orientation of the electrophilic attack. Alright, so now I'll go through. So the first paragraph is basically telling you that there are two for directing electron donating groups, and this includes alkyl groups. Basically, the first paragraph is talking about the very first row. This first row right here. So electron donating 2,4 directing groups will increase the electron density of the benzene ring and make it more susceptible to electrophilic attack. It also will direct the incoming electrophile to the second and fourth position relative to the carbon. Okay? And it will form a stable carbocation to disperse the positive charge. Alright. I think one way to appreciate this is I'll use phenol, and I'll show you how it actually even though most people know phenol to be the OH group to be electron withdrawing by inductive nature, but in terms of resonance, it will be able to help to direct the electrophiles to the second and fourth uh position of the benzene ring. So for phenols, it's electron withdrawing by inductive, and that is due to the highly electronegative oxygen. And this electron withdrawing group or electron withdrawing effect is actually weaker than the electron donating resonance effect. So 1 is less than 2, and that is why it's called an activating group. And we will always see that the electron density of phenol is much higher compared to benzene. Okay, so this explains the rate of ES to be high. Okay, so for now I'll do the orientation of the electrophilic attack. Okay, just to clarify this, most of these concepts are actually just to appreciate the concept. So most of the time you don't have to worry too much about this. You just need to concentrate on knowing how to use the data booklet to answer the questions regarding the effect of these groups on the reactivity of the benzene ring. Okay, so you can see over here that we will actually draw resonance structures. Can you see that my second position gets the negatively charged? And this will go over here. And now my fourth position will garner the negative charge. Okay, so this is how we always say that the second and the fourth position will garner the negatively charged. Alright, uh, my bad, this one should be a double bond. So a double bond and then another double bond. Okay, the second paragraph talks about the electron withdrawing groups. So the electron withdrawing groups withdraw electron density from the second and fourth position and makes the ring less susceptible to electrophilic attack and directs it to the third position to intensify the positive charge on the carbocation intermediate. So in this case, I will show you how it is being done. We'll use NO2 as an example. So for nitro, okay, wait, let's use a red pen. For nitrobenzene, alright, so we'll have, okay, I'll draw out the whole entire structure to make it easier. Okay, so one thing to take note is that it is both electron withdrawing by inductive effect because of the highly electronegative nitrogen atom, or you can also talk about the positive charge on nitrogen. Then secondly is electron withdrawing by resonance. Alright, so how this will work is that remember what I say, electron rich go to electron poor. So for this case, right, my lone pair on the oxygen will go, actually no, it won't go here. But we will use, because the NO2 group is our electron withdrawing resonance group, so the high bonding electron will be pushed towards nitrogen and cause the NO pi bond to be pushed to the oxygen to make the oxygen negatively charged. Okay, so you can see the second position now is positively charged, and that is why the electron density of the carbon on the second position decreases, and that is why it's most electrophiles when they approach the when most electrophile they approach the second position, they will repel away. So that's why they preferably want to attack the third position. Okay. I'll draw one more time to show why the fourth position is also not a good place to attack. So you can see the fourth position now is not a good place to attack. Alright. And that is why it is a three directing group. Okay. So I think one more thing I can talk about is how for the first paragraph, the second and fourth position relative to the actually no, I can talk about how it forms a stable carbocation to disperse the positive charge. I can use one accidental example which is methyl benzene. Okay, so example, you want to attack a electrophile. So maybe this electrophile we will name it E plus. Okay, so we will attack this slow step and I will form this product right here, E and H. Okay, can you see that this positively charged carbon is bonded to three electron donating groups? Okay, electron donating alkyl groups, so to say. So that's why this is actually a tertiary, I would say this one is actually a tertiary carbocation, and thus you can see that the attack of the electrophile on the second position carbon is actually preferable. If you want to attack it via, for instance, the fourth position, I can show you right here. So the positively charged is here. I can actually push the pi bonding electron pair such that I can still achieve a tertiary carbocation. Alright, and last but not least, I will show you the worst example, which is to attack it on the third position. So this will become positively charged if I shift here. I'll push the electrons here also. You can see I can only form secondary carbocations. So most of these are actually secondary carbocations, which is less stable than a tertiary carbocation. So this is why we do not preferably want to attack the third position. Alright, let's go on to the next paragraph. So for halogenation, the electron withdrawing effect right here is actually stronger than the resonance effect. And that is because the lone pair on chlorine delocalizes into the pi electron cloud of benzene ring to increase the electron density on the benzene ring. And you can see that Cl being period 3, the p orbitals more diffuse, less effective side-on overlap with the p orbitals of the benzene ring. Because the carbons of benzene ring, they are two p orbitals which are smaller compared to 3p orbitals of chlorine atom. And this is why I would say the keyword here, the extent there is less extensive delocalization. And thus chlorine would decrease the electron density on the benzene ring and cause the rate of ES to decrease. So the activating group and the deactivating group is always related to the rate of electrophilic substitution. Okay? And for the same case, I can leave it for you to draw as a practice. You can draw the resonance structure of um, chlorobenzene or bromobenzene. Then you can see how it actually shows that the negatively charged ends up on the second and fourth carbon. And that's why uh, you have your 2,4 directing effect. Okay? The last point shows how normally for the 2 and 4th position, we'll expect a ratio of 2:1 because there's two ortho position and there's actually one para position. However, because of steric hindrance, if you attack it at position 2, you will have a lot of steric hindrance. Okay? Whereas if you attack it at position 4, there's less steric hindrance. So the larger the size of the group on the ring, the greater the proportion of force substitution. So this table is good to remember. So I would show you over here. If the nitrogen and oxygen have lone pairs and that they have p orbitals overlapping with the pi orbital of the benzene ring, then you can have delocalization and this important concept called resonance. Okay, so that's why it's strongly activating. Your your alkoxy amides and ester groups are definitely less uh strongly activating because you have your competing effect. Okay, because you can see for amides and esters, the lone pair, you can imagine this is your benzene ring, right? This lone pair can either go here or go here and go up here because you can see this benzene ring, it can act as a electron withdrawing group. This C double bond O can also act as an electron withdrawing group. So there's a competitive, I would say that it's more of a competition. That's why it's less strongly activating right here. And as you can see for this alkoxy group, your R, you have competition between your benzene ring that is electron withdrawing and your R group that can be also be electron withdrawing. So Alkyl groups, I say already, is activating via inductive effect. Halogens, also I talk about it. Uh, Atoms with pi bonds to the electronegative groups. So as you can see over here, uh, if I have a C double bond O or S double bond O, uh, C triple bond N double bond O. So all this would be very electronegative and cause the electron density on the benzene ring to decrease via resonance effect. Okay, and if you have highly electronegative uh, atoms or positively charged atom right here, it will also cause the electron density to decrease by inductive effect. For this case, I will show you right here. Predict the major organic product for the following reaction. So I would say that, oopsies, what happened? Okay, so for this case, there's two activating groups right here, OH and C2H5. So in this case, we have to identify which one is a stronger activating group. So that table comes into very good use. So we now know that OH group is actually the phenol group is actually a stronger activating group, and thus it will direct the electrophile to this position right here, either the second position. So this is why the product one is produced in a larger yield compared to product two. Okay, I'll take a short break here and then we'll move on to the practice questions for Arenes.